Gas laws, this is where we combine all the individual gas laws to produce the ideal gas law. So if we take Charles's law, Boyle's law, Avogadro's law, and we combine them all together, Gay-Lussac's, Hamilton's, etc., and we combine them all together, we get PV equals nRT. Okay, oops. So what is PV equals nRT? Well, pressure, volume, N is the number of moles, and R is the gas constant. Now, this is the form of the gas constant you're going to be asked to use. And here's the thing. Wait, we said you could use any pressure you want, any volume you want. That was true before, but now, if you go through the gas constant, we have to be in liters for volume. Pressure has to be in atmospheres, and again, temperature still has to be in Kelvin. So that's going to dictate what our units are. So we're going to have to calculate the units that are needed as we do the ideal gas law. Okay? So again, it's always PV equals nRT. So what's the temperature in degrees C if we have these species? Well, temperature is what we're looking for. N is 0.32 moles of chlorine, happens to be chlorine gas. Volume is 2.7 liters, and pressure is 1934 torr. All right, so we're PV equals nRT. So remember the gas constant. So the first thing we have to do is get things in proper order. So our moles are fine, our volume is fine, our pressure is not. We've got to get it in atmospheres, so we know that there are 760 torrs in 1 atmosphere. So that gives us 2.54474 atmospheres. Again, significant figures being what they are, I'm going to tell you to carry 4 or 5 after the decimal place. All right, so we're looking for temperature. So if we take and convert it, temperature is PV divided by NR. Because in order to get temperature by itself, you're going to have to divide both sides by NR. So we get PV equals NR. So pressure is 2.54474 atmospheres. Volume is 2.7 liters. N is 0.32 moles. And R is 0.08206 liter atmospheres per mole K. Now, I want to warn you, you need to use whatever R value you've been designated with in different places, because the book uses 0.0021. I don't remember what mastering uses, but check and use whatever unit they ask for. So if we put this together, temperature is 261.65, 298 K, but I specifically asked for it in Kelvin. In degrees C, it's in Kelvin, so I'm going to subtract out 273, and I get minus 11.50 approximately. And actually, I didn't keep enough digits in that, so 261.65298 minus 273.15. We actually get 11,49702. Now, if I tell you that I only want it in 4 significant figures, then it would be a negative 11.50 degrees C. And again, I'll tell you how many significant figures I want here. All right, so what volume would 0.18 grams of oxygen occupy? Now, a lot of times you'll see me do this. I'm going to go down the columns, so I'm looking for volume. I know that I'm oxygen and I'm given 0.18 grams. We're just going to list what we have. Pressure, and this is actually, we're going to get to that one in a minute. Pressure is 1.2 atmospheres. Temperature is 19.5 degrees C, which we can convert to 292.65 K. So the only one we're really missing is moles. Well, guess what? If I take 0.18 grams of oxygen and divide by the atomic, in this case molecular weight, which is 2 oxygens per 1 mole, then we end up with 0.0056252 moles. So what that allows us to do, if we're playing with PV equals nRT, that means this is our one we're looking for. We've got this one, we've got this one, we've got this one, and R is a constant. So volume is equal to nRT divided by P, because I isolate V by dividing both sides by P. So that's 0.0056252 moles. And I'm going to run out of room, 0.08206 liter atmospheres per mole K. And I'm going to cheat and come back over here and put in my temperature and put my equal sign. So 292.65 K divided by 1.2 atmospheres. That means we end up with 0.112574 liters. I didn't specify. If I don't specify, you can give it to me in liters. But if I say I want 4 significant figures in milliliters, then you would give me 112.6 milliliters. Okay, easy peasy. Again, the problem with these are twofold. One, you've got to remember to convert temperature to Kelvin, and 2, you have to do your algebra. Now, a modification of the ideal gas laws is to determine density. And this is actually really easy. And I'll double check the formula sheet. I'm pretty sure it's there, but I'll show you how you can walk it through and solve for it. So we have our ideal gas law, and we know that this is a symbol for density. So density is mass over volume. And later we're going to do moles as grams over molecular weight. But we're going to need it now as well. So if we go ahead and put in the moles, for moles we put in grams and molecular weight. So all we did was substitute in this one. So then that allows us to rearrange. And in the book they're going to use for molarity, molecular weight, they're going to use a kind of stylized M. I can't do that. So I'm just going to use molecular weight. So here we have PV equals grams RT molecular weight. Now, how do you get to the other side? Well, basically we need volume brought over and all these other ones brought over to the other side. Now remember, if we're going to move them and they're in the denominator, they go in the numerator. If we're going to move them in the other way, it's RT molecular weight. So that's why we end up with pressure times the molecular weight is equal to RT, which this is the density. So why is that important? Because grams and volume, that's easier to measure in lab. You can measure the grams of the gas and you know the volume it's in, or can measure the volume. So this is a great way to do this. And the other flip side of it is now we've introduced molecular weight, so we can solve for the molecular weight, which brings us to solving for molecular weight. Again, we're basically going to make this connection. We're going to set N by itself, so it's PV equal RT. So if we substitute in this here, we get this species. So all we have to do is remember, we multiply both sides by the molecular weight, divide both sides by PV, cancels that, and you're left with molecular weight is grams, gas constant, temperature over PV. And that's the symbol they use for molecular weight. Okay? So, the beauty of this is we've done 2 things. Well, we've actually done 3 things. It allows us to calculate density. it allows us to calculate molecular weight, and allows us to calculate grams if we need them. So let's do some. So we're told that the density is 1.96 grams per liter. And there are a couple ways you can do this. More about that in just a second. Temperature is 0 degrees C, which is 273.15. Pressure is 1 atmosphere. And we want to determine the density per liter at 65. Oh, wait. So pressure 2, we want the new density. So we're going back, and these are all ones. So we have a pressure of 650 torr. And we have a temperature of 25 degrees C, which is 298.15 K. So wait a minute. We said that PV is equal to nRT, and N is equal to grams per molecular weight. So PV is equal to grams per molecular weight. RT. So if we move everything that's to the other side, so if we put what's not changing? Okay, R isn't changing. So we do 1 over R is equal to grams divided by volume. We're just going to call that density. T over P and molecular weight. Okay, so the beauty of doing that is, wait a minute, that's a constant. So what we end up with is, oh wait, the molecular weight stayed the same. So it's coming over here. So we have molecular weight here. We don't have it here. So what we're saying is that we have density 1 over T1 is over P1 is equal to density 2 over T2 over P2. So what we have here is just a simple conversion. And so if we're looking for density 2, it's equal to P1, T1, P2 over P1, T2. All right, so we know our first density, which is 1.96 grams per liter. We know our T1, which is 273.15. Okay. We know our P2, which is, oh, crud, we have a problem here. But we're not going through R, so the simplest fix is 760 torr here. And so P2 is 650 torr. Now you could have converted those both to atmospheres, that's fine. And T2 is 273.15. So what we've got here is, when we solve for it, we end up with 1.53576 grams per liter. Actually, it's not grams per milliliter. Pay attention to your units. Ha ha ha. So again, if we had 3 significant figures, we would report it as 1.54 grams per liter. Okay, so that's how we would do a density conversion. And that particular one didn't require us to go through ideal gas law. We're actually doing a comparison, so we were able to cancel things. All right, so here the density of the gas is found to be 1.045 grams per liter at STP. So wait a minute, that means standard temperature is 0 degrees C, which is 273.15. And pressure is 1 atmosphere. What is the molecular weight? Okay, so PV is equal to nRT. N is grams per molecular weight. So PV equals GRT over molecular weight. So wait, we're looking for the molecular weight here. So the molecular weight is equal to G divided by V RT over P. Okay, so in this case, our density is 1.045 grams per 1 liter. R is 0.08206 liter atmospheres per mole K. Temperature is 273.15 K. And pressure is 1 atmosphere. So if we look at it, our liters cancel, our atmospheres cancel, our K's cancel, so we're left with grams per mole. So we end up with 23.42335 grams per mole. If we're using 4 significant figures, then it's 23.42 grams per mole. Okay? So the next one is what's the density of butane? At 45.2 degrees C. So first things first, as I go along, that's 318.35 K. A 24 torr, we're going to go through the gas law, so we need to take 824 and divide it by 760, which is 1 atmosphere. So that will give us 1.08421 atmospheres. So we want the density, and remember the density is going to be grams per volume.